Let's talk about my operating system, Redacted OS. This is an operating system hobby project that I've been working on for the last few months. And in my last video, I talked about how I finally ported it to work on the Raspberry Pi 5 running on real hardware. So how's that going? Have I kept working on real hardware? Well, not really. I actually have been making new changes to the system, not on real hardware, and once I tried to run it on real hardware, yeah, it's similar error to one I mentioned in the last video, BE000011. Last time it was 411, which stood for unrecoverable. Now it doesn't necessarily mean that anymore, it's just 11 instead of 411, but it's still an error. And honestly, I have other things to focus on, so I'll fix it next week probably. Moving on, we're going to talk about terminals. Okay, our terminal is not going to look like a fancy airport terminal. It's more so going to be a bus terminal, if you will. But what are you talking about? Airports, buses? Okay, let's actually talk about what I mean. This is a terminal. Now, this may not be what you think about when I talk about a terminal, but this is technically what a terminal is. Nowadays, if you talk about a terminal, you're more so referring to something like this. A virtual terminal or a terminal emulator. It's supposed to be emulating that machine that we see on the left, but it pretty much works as a terminal, so we just call it a terminal. And today we're going to be creating one of these for Redacted OS. Now, if you've used Linux, Mac, or some other similar operating system, you may have seen these commands before. ls for listing the contents of a directory, cd for navigating directories, and for seeing these mkdir for creating a directory, cat for opening a file, or mv for moving a file, which can also be used to rename files by just changing their path. And yes, on both Mac and Linux, these commands are always the same. There can be small little changes in how they work, but the name of the command and the overall way in which they work tends to always be the same. And you may already know where I'm going with this. The reason these are the same is because they conform to the PZIX standard, or the Portable Operating System Interface. This is a standard that was created for operating systems to conform to in order to make them more familiar. And actually, PZIX is a standard that is part of the Single Unix Specification, or SUS. Sorry, I know it's a 5-year-old joke at this point, but I just have to make it, you know? Some things just have to be done. Now, the Single Unix Specification talks about Unix, and Unix is an operating system, or a series of operating systems, started all the way back in 1969 by Bell Labs. Systems that conform to the PZIX standard tend to be called Unix-like, because they follow all these standards that were set by Unix. Essentially, they replicate an operating system created in 1969. They don't replicate it one-to-one, obviously, and they have modernized themselves, but they do follow this standard to, well, standardize the way that they work. Now, I'm mentioning all this because it is important context for what we're going to be talking about, and honestly, I have taken plenty of inspiration from the POSIX standard and from Unix in order to create my system. And in fact, a lot of the commands that I either have implemented or will implement will have the same overall names and usage as their POSIX counterparts, like ls or cat. But that doesn't necessarily mean that I'm going to be conforming to the POSIX standard. Maybe in the future I will want to bring my system up to standard, but for the time being I'm not really concerned with that. And I don't necessarily want to constrain myself to following a standard. The good thing about the fact that this operating system probably will not at any point replace any of the big 3 operating systems means that I don't have to make it compatible with those 3 systems. And while I want to make some things work the same way, or obviously I'm taking inspiration from my own knowledge working with these systems, I don't necessarily have to replicate the POSIX standard, and I can just do my own thing. And as a matter of fact, in order to bring my system up to POSIX compatibility, I don't just have to create a bunch of commands with specific names and specific usage. I actually have to do a lot of other things. Certain syscalls, the way that the shell works, which is what we just talked about, but also threads or the C standard library and a lot of other things have to be brought up to standard. So like I said, I may be taking inspiration from Unix, but it's not the only place I'm taking inspiration from, and I'm not closely following the standard. And actually, another place from which I'm taking inspiration, which is very closely related to Unix, it's in fact its little brother, is Plan 9. An operating system also created by Bell Labs to be the successor to Unix. Now, this operating system is more of a research operating system for developers to test out ideas and develop. It's not really meant to be used as a daily operating system. Even more modernized forks or versions of it, such as Inferno or Ninefront, aren't really meant to be used daily. But even then, they have inspired me plenty in how I want to design my system. As a matter of fact, I will be talking about Plan 9 a lot in upcoming videos, but we're not ready for that yet, so let's move on. All that to say, my system may be inspired by Unix, may have some elements that come from Unix. I don't know if that would make it Unix-like, to be honest, but for now I'm calling it non-Unix. And actually, it's not just me, it's Wikipedia. Wikipedia is calling my system non-Unix. So what can I do? I have to do what Wikipedia says. All that to say, I may take inspiration in some of the names of the commands and even some of the overall system structure, but I'm not necessarily going to follow it strictly, and I'm going to opt with going my own way instead of following a standard. Okay, let's actually get to implementing this terminal. So you may remember from my very first episode, I talked about having a visual console. When you first boot into the system, you see this screen that just shows you information of what's happening while the system boots. After the screen disappears, there's a UI, but you get to see this for a few seconds. And the class that powers this is already a class that draws characters on a screen following certain rules, and actually, it's perfect for our terminal. So we can just create a new one. It won't be connected to the console, so it won't be showing logs from the system unless we want it to, but it works in more or less the same way, and actually, the terminal class that powers it is a subclass of the kernel console that powers the initial boot one. Before we actually build a terminal on top of it though, I have to expand it with a little bit of more extra functionality. First off is a cursor. So far we've just been printing information to the screen. And actually, this information scrolls by really fast. You're not necessarily supposed to be reading it. It's just there for debugging. If at any point the system fails, then you can see what's happening in it. But now, we want to be able to type to it. And one big important part about that is knowing where we're currently typing. We want a cursor. And as a matter of fact, the way that the console is built, it already has a cursor. It already keeps track of the next place in which we will write a character once we actually need to write that character. But we're just not showing anything visually. So it's pretty simple for us to just draw in a rectangle in that place, and now we have a cursor. We could make it blink, but that would require the use of some kind of timer, and my system is not exactly set up for working with timers. I could fake it in other ways, but they would not be the best, and honestly, it's not that important to make it blink, at least for this initial version. Another thing that would be pretty important for us to do is deleting characters. If we make mistakes, we want to be able to delete the characters that we've written, and actually this is pretty simple. We just move the cursor back by one spot, and then we delete the character that was there, and we redraw our visual cursor so that it keeps track of that. It gets a little bit complicated when we need to go back one line, because in that case, we need to know where the cursor was, and it's pretty simple to do. We just have to find where the string that represents the previous line ends and put the cursor there. But if you've ever used a terminal before, and most likely if you're watching a video about operating system development, I can assume that you used one at some point, then you may know that they can have some fancy features, such as colors. Now, the way that these systems implement colors and the way that I'm gonna do it are not exactly the same, but of course, my way is inspired by theirs, and so I'm gonna talk about it. You remember when I used this image? This is not just some random terminal I found online and put a picture in my video. This is actually the VT100. This is a terminal that introduced something called the ANSI escape sequences. These are a special set of characters that have special behavior within a terminal. And because most terminals nowadays in modern computers are actually terminal emulators, they're emulating real terminals like this one that have these escape sequences, and so they have this extra functionality. And the functionality that we're going to be looking at right now is text color. So to set the text color in the VT100, or for that matter on Linux or Mac, it looks like this. We start with the escape character followed by 033, which is actually an octet number, which indicates the beginning of this escape sequence. It's then followed by an opening bracket, which indicates the type of sequence that this is. Then it has this 34 number followed by an M. The 34 is the color. Now, the 3 actually stands for the foreground color, or the text color, to make it simple. The 4 stands for the fourth color. So what's the first, what's the second, what's the fourth? What's going on here? Well, there's a list of colors, and the color that we're showing here is the fourth one. So obviously this is a standard that has been going since the 1970s, but honestly, I found it to not necessarily be the most intuitive. And like I said before, I don't expect this system to replace Linux or Mac or Windows. Honestly, anything's better than Windows, but mine just doesn't have that many features just yet. But either way, I don't necessarily need to keep compatibility with those systems and my own. And when it comes to following a standard created in 1970 for 8-bit colors that's since been progressively updated until it got to 32-bit colors, but honestly it's no longer the most elegant, or just creating my own for my own hobby operating system, well, I'm gonna choose to create my own. The redacted escape sequences. It's not actually called that, I'm just calling it that for the video. And obviously it's still inspired by the ANSI escape sequences. We start with an opening bracket. I would have loved to start with the 033 octet, but as a matter of fact, my terminal is kinda dumb for the time being, and it cannot recognize that \033 is an escape sequence and represents just one character. It considers them 4 different characters, and that makes it a little bit difficult to parse. So for the sake of simplicity, we're just going to use an opening bracket to start our sequence. And sure, in the future this will present some sort of ambiguity, because opening brackets can be used for other things, but right now my terminal is so simple that this doesn't really create any kind of ambiguity. And hopefully, if it ever does, then I will have already expanded my parsing capabilities in order to properly detect more complex escape sequences. For that matter, I might actually implement ANSI escape sequences in the future. It just didn't seem too important to implement right now. Again, keep in mind that pretty much everything that I'm saying for the system is not set in stone. For example, I mentioned that the system was going to be a gaming-oriented console-like experience. Obviously, gaming console, not this type of console that we're talking about right now. But now I'm aiming towards a more multi-purpose OS. So, like I said, nothing is set in stone and everything is open to revision. Oh, that's a big tangent to go on when I'm just talking about escape sequences. Alright, let's get to the next part. After that, we have a hexadecimal number followed by a semicolon. That's how you define colors. It's pretty simple. Opening bracket, hexadecimal color, semicolon. This will set the text color from now on until you finish the command, that is, you press enter, by the color defined by this hexadecimal. So again, not a standard compliant solution by any means, but a simple one that works for what I'm trying to do. Okay, let's create our first command, cat. Cat opens a file, and for example here we can see that we're trying to open the dev console. Now, this is a pretty simple command. Again, if you've used a terminal before, you've probably used a cat command at some point. It's pretty easy to understand what's happening here. We would be reading the contents of the console. But actually, when you're developing an operating system, these 3 words and 3 characters, if we count the space, actually represent a lot of different things that you have to create. First off, how do we differentiate what's the command and what are the arguments? How do we parse each of them? How do we execute the command? Alright, that's a lot of questions. So let's start. How do we separate them? Well, for the time being, we just separate them when we find a space. Now, I know that technically you can have escaped spaces using a backslash, but again, not really a thing that I'm supporting right now and not really necessary for the time being. Once my parsing capabilities get better, then that will also improve. But for the time being, we just find a space and everything to the left of it is the command and everything to the right of it is arguments. Those arguments can have spaces. It's just the first space that is counted. And actually, if we run this command, we will get the console, the same one that we would get at boot, showing up in our new terminal, the one that shows after we've put it into the system. But wait, how did you do that? Alright, first off, the cat command. Where did that come from? Well, at first, I was just faking it. I created a function within the terminal called tmpcat, stands for temporary, because I never really intended it for it to be this way. I just had to change some other things within my system in order to make it work properly. So the first version worked like this. It had a function within the same terminal that would open a file and print out its contents to the terminal. But why did you need a function? Well, let's talk about the way that it's supposed to work and the way that it works now. Our command would be placed in a place like this, /bin/cat. That's where we find the command. And actually, bin is one of the directories that the terminal will go to in order to find the command. It actually has a list of directories that it looks in. They're called the path I don't really have support for this right now, but that is the way that it works on other systems. For now, in mine just looks in bin, and there it expects to find a command called cat, and then it executes that with the arguments that we pass to the right of the space. So in this case, dev console. But okay, let's say that we have this cat somewhere in this bin folder, and the cat opens dev console and prints out the file. And then we have our terminal. How do we connect the two? At the beginning, there was no real way to connect the output of the process into the terminal, which is why I was using this fake function within the terminal, because that way I could directly put the output of the process into the terminal. But the correct way in which I'm doing it right now is by accessing the cat process's output, which can also be accessed as a file, as proc3out. And the output can now be wired into the terminal, so showing us the content of the file that we're trying to open directly in the terminal. But wait, /dev/console/bin/cat/proc/3/out, are these files on your system? Are you telling me that your processes are files in the system? The console is written directly to the disk? What's going on here? Well, this is where we talk about another philosophy that I'm very much borrowing from Unix, and also from Plan 9, which expands on it greatly. Everything is a file. So this philosophy simply means that system resources, such as the console, or process information, such as its output, are all presented as files. Now, they're not actually files on the disk. They're actually files in something called the virtual file system, or VFS. So they're not really on the disk. The system just exposes them as if they were files, but they really aren't. So, okay, they're files, but they're not really files on disk. So how exactly are they files? And what is a virtual file system, and how do you implement something like that? Well, I did it through something like this, a driver module structure. Essentially, any system resource that I want to expose as if it were a file, I expose through this interface. It's simple, a name, just something to identify the module. For example, for the console, this would be console, followed by a mount point. And the mount point indicates how we access this resource. For example, the console is mounted to /dev/console. Processes are mounted to /proc. After that, we have a version number and an initializer and deinitializer, even though I don't really use the deinitializer. The version number is there for compatibility, and the initializer is there for, initializing the driver. But what comes after is the part that powers the whole everything is a file philosophy. We have functions like open, read, write, seek, and read dir, which stands for read directory. Essentially, each driver defines what happens when you try to read a file within its mount point. For example, if I try to access /proc/3/out, how does that work? Well, the process modules will determine that because it is mounted to /proc. So my module loader, responsible for keeping track of all these modules and initializing them, will transfer any requests that go to /proc/something else to this module. And for example, if you try to read from /proc/3/out, then you will trigger the read function. If you try to write to it, you will trigger the write function. And for example, if you try to read the contents of the directory /proc, it will give you a list of all processes running on the system. So with this, we can kind of understand how our terminal will be able to read the contents of the cat process's output, which will output the file /dev/console, and in turn, how the cat process is going to access the console through /dev/console. Essentially, when cat tries to read the file, it will open a file located at /dev/console. This request will be sent to the console module, which has its own logic for handling accessing the console. In the future, it will be able to only let you access your own process's console unless you have privileged access to the entire system's console. But for the time being, it lets you open the system console as a file. Then the cat process will read the contents of that file, and you will notice that it actually uses a file descriptor, this file structure that I'm using, which is simply a unique ID and then information about the file, such as a cursor indicating where you're currently reading or the total size of the file. And then cat will write to its own /out for its own process ID, and the terminal will be able to read that in order to read the output from cat, and that's how we will display the output of the cat process into the terminal. I really love it when things come full circle because this terminal class started out as something that we used to read the console while booting. And now, well, we've added a bunch of functionality on top of it, but at the end of the day, we're still using it to read the console. But actually, with this kind of functionality, we'll be able to do a lot more things. Now, these are not things that I have currently implemented, but they're things that I'm in the process of implementing. It just takes time. For example, we could expose our networking interface through files. /net would be the mount point for this networking module, and then the TCP directory would contain all the TCP connections for the system if we access it with privilege, so that is to say from the kernel. If we instead access it from a user process, we can see our own connections, but not anyone else's. Then we can target a specific connection. In this case, I chose number 3. This isn't a port or anything like that, it's just a unique identifier for a connection. And finally, we can target this virtual file out. We can write to it in order to send packets through this connection. And we will have to configure the connection beforehand to tell it which IP it is connecting to and which port it is connecting to and from. All the stuff that I talked about in the networking video. But we might be able to do that through just a file instead of a specialized networking syscall, which is actually something I never implemented in my system. Another example is audio. I've actually been working on an audio driver, but I haven't really finished it, so that's a topic for another video. But once it is finished, I will be able to expose it through /audio/out, where /audio will be the mount point for the audio module. Then out indicates output devices, such as speakers, headphones, and whatnot, and 1 is simply an ID identifying a specific device. For example, the speakers on my computer. So by writing to this virtual /audio/out/1 file, we'll be able to create sound that goes to the speaker. If we target a different device, such as out/2, then that sound will go to the headphones. And if we use read there, or we try to read the directory /audio/out, we'll get a list of all audio output devices and choose the one we want. Finally, another thing we can do is get the input for the system from /in/kbd, which is the keyboard input. Again, this would be limited for a process only reading its own input, not reading the whole system's input, which is already how it works right now, except right now it uses a dedicated input syscall, whereas here it could use just a file. Now, I'm not saying that my syscalls are going to go away necessarily, but I am considering favoring a system like this one because you can do a lot of interesting things with it and interact with a lot of the system without needing to have specialized syscalls for that. And actually, you can combine these in interesting ways. For example, we already saw how we can combine bin, cat, and dev console to read the console in our terminal. So that's a pretty simple one we already talked about. But what if we wired a keyboard into the output of the audio? Now, this wouldn't be done directly, obviously. You would have to have some sort of program that interprets keyboard output and maybe transforms it into MIDI notes, which it then transforms into audio waves, which it then outputs to the audio device. In the same way that the cat process is processing the dev console and outputting that to the terminal. Another thing you could do is, for example, wire the output of a process, so /proc/3/out, into a pre-existing network connection, such as /net/tcp/3/out. Or maybe UDP would be better for this type of thing, but essentially you could put the output of the program as a UDP or TCP packet transmitted through the network to another computer. So remote logging, all done just by connecting two files, without needing to create any special functionality for it. Hell, if I expand my terminal a little bit more, we'll be able to do this entirely through the terminal. Now, obviously, everything that I'm mentioning here will need some kind of processing. Like I said, you don't just immediately send keyboard output to the audio and expect it to play music. You have to have some sort of program that processes all that information. And for example, it could look like this. This is using Unix pipes, which I currently don't have in my system, so this is more of an example. Although you can technically do this with code, Unix pipes simply make it very easy to even do in the terminal. So you could read the contents of /in/kbd in order to get access to the current key presses. Then you can pipe that into a synth program, which takes those, processes them, and creates audio waves, and pipe that into the output of the audio. Now, obviously, any decent synth program would already have some internal way of capturing input and producing output, but this is just an example. This way, you could make it do things that it wasn't really expecting to do, or that maybe there aren't specific syscalls in the system to allow you to do this. But like I said, pipes are not something I currently have, and actually the more I talk, the more I realize my system is becoming Unix-like, even though I continue to remain delusional, really, and say that it's not Unix-like, but little by little we're getting there. Still, I'm not too interested in conforming to a standard. Like I said, this actually results in simpler syscalls. We don't have to have a specific syscall for reading or writing to the output. Obviously, we need to have functions to do that because you don't want to have to open a file or write to a file every single time you want to write a log on your program. And in some cases, syscalls that directly simply write to the console would be more efficient. But again, this virtual file system and exposing system functionality through a file system instead of just through syscalls allows us to do things that maybe the existing syscalls don't allow us to do. Ironically, until very, very recently, my system did not have syscalls for reading, writing files, or opening them. So at the end of the day, I needed to create more syscalls to power this whole thing, not fewer. But like I said, the point is not to replace syscalls, but to provide an alternative to them. And actually, when I first look at the driver module, which is inspired by the Linux driver module, a similar structure to the one I showed, I was a little bit skeptical that you could possibly have any kind of driver on your system represented by this interface. But then I remembered something very basic and simple from computer programming. At the end of the day, computers are data processors. They take input, they process it, and they produce output. Not only are computers that, but so are our kernels and the drivers that power the peripherals and even the kernel itself. At the end of the day, everything in computing works like this. It takes an input, it processes it, and it produces an output. And if you look at the driver module, that's exactly what's happening. It takes an input by the write function, and it produces an output that can then be retrieved through the read function. Anything else besides that is just fancy wrappers or management or convenience, such as the open function, the seek function, and whatnot. And with this, we've reached the end of the video. I started out this video saying my system was not very Unix-like, but the more I narrate, the more I realize that yes, it is pretty Unix-like. It just isn't PZIX compliant, and I'm not trying to make it a PZIX compliant. So maybe Wikipedia needs to be updated. But hey, I'm on Wikipedia, that's pretty cool. With that being said, some channel announcements. I'm actually rapidly approaching 10,000 subscribers, and my community has been asking what I'm going to be doing once I actually arrive at 10,000 subscribers. I asked what I should do, and I got some unrealistic responses like a week-long live stream. Another interesting alternative that was suggested was porting Doom to my system. This is something that I had plans to do a while ago, but I haven't actually gotten around to it. And like I said, I've been working on an audio module, and audio is pretty important for games, I think. Funnily enough, the mouse is not. The game can be played entirely with a keyboard, but audio would be pretty nice. So now that I'm starting to work on a driver for that, porting Doom would actually be an interesting idea. Let me know if you would be interested in seeing this for a 10K special, or if you have any more ideas, and please keep it reasonable. I'm not doing week-long live streams. But speaking of live streams, I have been live streaming for the past few weeks on Twitch. I enjoy it quite a bit, even though I don't necessarily have a set schedule right now. I'm experimenting with creating a schedule, and I plan to do it a lot more. Everything that I talked about in this video, I actually developed on livestream. So if you're interested, I do them on YouTube. You can turn on notifications to see them. I also have a Twitch channel, which I've linked on my YouTube and in the description of the video. And of course, I also have a Discord where I talk about upcoming live streams, and you can even sign up to get notified for these live streams and for new videos that I post, as well as talk in a more personal manner. And finally, I mentioned in my last video, I was going to start doing write-ups, and I haven't really started with this yet. I kind of have an idea of where I want to go, but honestly, I've been more focused on development of the actual system and making these videos and live streams and all that stuff, more so than doing write-ups. But it is something I'm interested in doing, so stay tuned for that. I'm hoping the first one comes out very soon. And with that being said, this is the end of the video. Thank you so much for watching.